Hello everyone, welcome to the fourth lecture on reinforcement learning. This lecture is going to be on dynamic programming. So previously we looked at how to formalize the reinforcement learning problem as a Markov decision process, but we didn't yet learn how to actually solve those Markov decision processes. So from now on we're going to, and for the rest of the course, we're going to look at how to actually solve them. So we're going to study the kind of algorithms that we can use to build agents that learn to behave optimally in an environment. So during this lecture, we're going to look at an implementation that actually solves an OpenAI Gym environment using dynamic programming. And we'll connect it to some of the definitions covered previously to hopefully build a kind of richer and deeper understanding of them. And this course is very much just going to layer and layer and layer. And then through the next lectures, we'll layer on top of the concepts introduced for dynamic programming, the ideas here that we have of policy evaluation, policy iteration, value iteration, and we'll just build more and more sophisticated techniques which allow us to solve more and more complex, deeper and more difficult environments as we go through. But the underpinning theory and concepts you learn today will sort of carry through into future lectures. So before we get to an actual definition of dynamic programming, let's just examine why it's called dynamic programming. So just breaking up the words themselves, dynamic means we're talking about problems which have sequential or temporal characteristics, so over time. And programming, well, the word programming here is used in the mathematical sense, as in linear programming. So we're talking about the field of mathematical optimization. And in our case, we're really talking about optimizing a policy of an agent. So you can think of it as optimizing sequential policies or learning optimal policies over time. And that is, these are collections of algorithms that are used to compute optimal policies given a perfect model of the environment, such as an MDP. Now onto the actual definition. So dynamic programming is an optimization method for sequential problems. So dynamic programming allows us to solve complex planning problems. So for example, just looking at the image here, there's this mountain hiker who needs to navigate some difficult terrain to reach their goal, which is the summit at the top of the mountain. And there's some terrain along the way, which is kind of too hilly or too rocky. So some of the terrain is hazardous and there's some probability that the mountain climber will fall off and break their legs. But maybe there's like a shortcut along the way, which avoids that terrain, or maybe it goes through some terrain. So basically the mountain hiker needs to solve this planning problem, and dynamic programming tells us how to behave optimally. So long as we have the map, so long as the mountain climber has got good experience to figure out what the probabilities are of breaking their leg, then we can figure out how to plan our way through this environment, considering all of the dynamics of the environment, that the ice might break, that you might slip on the rocks and break your legs. It helps us to plan through and find an optimal route through it. So this can generally be achieved with two principles, and that are that we break the problem up into smaller sub-problems. So dynamic programming excels in any situation or problem that can be broken down into sub-problems that can then be solved individually and then reassembled back together. So that's the first principle, breaking the problem up into sub-problems. And the second principle is to cache and reuse the optimal solutions to the sub-problems to find out the optimal overall solution. So for example, in this map here, in the mountain climbers map, they can work out how long it takes to walk along particular paths, which are optimal, and then so long as they can find their way back onto the path, they can reuse those calculations. So if you found like a flat trail here, you work out the optimal time it takes to move along that trail under optimal conditions. Once you've calculated that, so long as you can get onto this trail, even if it's very slow to get onto it, you can reuse that calculation to map out the entire path. And MDPs, Markov decision processes, they satisfy both of those conditions. So they can be decomposed into sub-problems, and the value function itself can be cached and reused. And if you remember the Bellman equation from week 2, this tells us how to break down the optimal solution for the value function into two pieces, which are the optimal behavior for one step, followed by the optimal behavior for the remainder of the trajectory. And the value function itself is the thing we store in cache. So that's like the person here with the map marking the value of different points on the path, and hence those values can get stored in the map itself, and we can reuse them to work out our way or work out the value of the other connected paths. So why do we bother learning this process? Why do we learn dynamic programming? Well, apart from it being a foundational part of reinforcement learning, dynamic programming can help find optimal solutions to many real-world problems, like managing your time and money, managing complex control problems, and so on. So let's look at a few examples. First of all, just looking through the slide, we've got Dijkstra's algorithm. And Dijkstra's algorithm, you've probably studied it before. It's a very famous algorithm, and I'm sure you've probably encountered it in your first year here in computer science. But effectively, it just helps us to find the shortest path between nodes in a graph. So, Dijkstra's algorithm can also be considered as a type of dynamic programming method, which relies on greediness to pick the order in which the subproblems are solved. Another one you've now encountered briefly in the machine learning lectures, in the deep learning lectures, is backpropagation. So here's where we want to compute the gradient of the loss with respect to all of the leaf nodes in a computational graph. And we want to reuse the previously calculated partial derivatives along the way to reduce the overall computation. So there are lots of cases, lots of other examples. If we just do basic maths, we tend to actually do this in our heads without really realizing it. So let's just try and think of like a nice example to make this concrete. And there's a really nice example that goes around by someone called Jonathan Pawson. And he gives this example where he says, just speaking in a metaphor, a child asks, "Daddy, can you explain dynamic programming to me?" And then the father writes down 1 plus 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 1 on a sheet of paper. He says, "What's that equal to?" And after some time counting, then the child says 8. And then he writes down another plus 1 on the paper and says, "What's that equal to?" And she immediately says 9. And then says, "Well, how did you know that so fast?" "Well, you just added one more." "So you didn't recount because you remembered that there were 8. Well, dynamic programming is just a fancy way of saying remembering stuff to save time later. So really, it's just recursion and common sense. The common sense is whatever problem you solve, you should first check and see if the same problem has already been solved before. It's cached in memory somewhere. And if it's not been solved before, then only solve it and store the solution somewhere for later reuse. And this trades the computation time for additional memory usage. So today we're going to solve planning problems in MDPs. I'm going to try and solve the planning problem. And this is not the full reinforcement learning problem. It's where you don't have a complete knowledge of the environment. We're just going to be trying to solve the planning problem, which is where you're given complete perfect knowledge of how the environment works. So someone tells you the transition structure, someone tells you the reward structure, and you want to solve the value of it to determine the optimal policy. So given an MDP, if you recall from the previous lectures, we have these states. We have A is the finite set of actions, and then we have the P, which if you remember was the state transition matrix, which tells us the probability of advancing to the next state, conditional on the current state under a given action. Then we have the reward function, and this tells us the expected reward conditional on a state and an action. And then lastly, if you remember, we had this discount rate, this gamma, which was the discount rate on the interval 0 to 1. And also for a given policy pi, if you remember. So for example, our mountain hiker, if they randomly are walked around as if they have had one too many beers, then this will be one policy of navigating the environment. Or if you remember, maybe they're a very experienced mountain climber who have developed a very experienced policy which ensures that they eat the right foods, they prep themselves, they wear the right climbing gear, and they stick to straight paths, they avoid sharp rocks and hazardous cliffs that they can fall and break their legs on. So you can have different policies. And we're going to work mainly today on how we evaluate these policies, and then later we'll solve the control problem, which is where we actually optimize the policies. So the first thing we need to do is know how to evaluate the policy so we can know if it's better to be drunk or whether it's better to follow the path. So given a policy pi, how do we know whether it's better? And then, like I said, we'll then work on the control problem, finding the best policy. So the optimal value function, V star, actually corresponds to the optimal policy. There's a kind of correlation. So there are kind of two strategies or algorithms to optimize this behavior to find out whether it's better to be drunk or to follow the path. And these are called policy iteration or value iteration. And they both rely on this policy evaluation function, which is basically some inner loop where you need to keep experimenting with new policies to see how good they are. So in this lecture, we're first going to study the policy evaluation approach, which is the prediction problem, and then we're going to look at each of these strategies to find the optimal behavior of the agent, which is the control problem. And we'll solve this using the Bellman equation that we studied on lecture 2. So if you remember, we had this there was like different variations of the Bellman equation. We had the Bellman expectation equation, which did an expectation over the actions. We also had the Bellman optimality equation, which did a max over all of the actions. And for doing policy evaluation, we're going to be using the Bellman expectation equation. And then later on, when we want to do control and find out the optimal policy to actually navigate the environment, to work out whether, what the best behavior to have is, which we're assuming isn't going to be drunk behavior, then we're going to use the Bellman optimality equation to do the control part. So to explain and show you the policy evaluation algorithm, I'm going to introduce the Frozen Lake OpenAI gym environment. And the concept is basically that you're playing Frisbee, and your Frisbee falls onto a frozen lake. However, some of the ice is melted, so you could fall in. And what's even worse is that the ice is really, really slippery. And it's so slippery that if you take an action, so you decide to move left in this little grid world here, or you decide to move in some direction, let's say you decide to move up here, then the chances are you're just going to fall over and end up slipping into a completely different direction. So this represents like the dynamics of the environment. So yeah, to model this metaphor, we use this kind of grid world idea. It's the environment model in Sutton and Bartow's book. And in the simple case, it's just a 4x4 grid of tiles, which are indexed from 0 to 15. And we wish to move from the start state, this green state over here, to the terminal state in red, which is where the Frisbee is. You can see we can basically set some reward in any of the cells, so we could put reward here or reward wherever we like, really. But genuinely, in the general case, it's 0 everywhere. The reward is 0 everywhere in all of the cells, in all of the states, except for the state where the Frisbee is, and we just set there's a positive 1 reward here. And also we can say this later on I'll show we have some ice, and if you fall in the ice, that's also considered a terminal state, and you'll lose if you fall in the ice. And there's lots of ways you could define reward in this grid world environment, beyond this Frisbee example. For example, you could have negative reward for every action you take, and then the terminal state of getting the Frisbee is just going to be trying to take the shortest path through it. It's probably worth saying for this first example, we're just going to ignore all of the slipperiness mechanics because they tend to make the solution very unintuitive. So in our case, when you take an action, you're always just going to deterministically transition with probability 1 to the next state, and that's the state you intend to go to. But in the OpenAI gym, and there's some Colab code that accompanies this, you can actually disable that determinism and have a look. But be really warned if you do try this. The results that you'll get will be optimal, but they will just look absolutely ridiculous. They will look so crazy and unintuitive that it just makes no sense to our human brains unless you really spend ages to see how the dynamics work. It'll be like, to get to this red square, you need to sort of walk backwards, slip on the ice, which takes you into a different tile. It just makes almost no sense, but it is optimal. So that's also, again, just like we talked about, how sometimes the optimal solutions can be very surprising if they are considering all of these crazy environment dynamic rules, like the rule of slipping on ice, how counterintuitively you might want to go in a different direction depending on what those probabilities are. Okay, so you can see here we kind of set up. Maybe I can actually just have a quick look at some of it. So this is actually what some of the collab code looks like, and once you connect to it, you can run some of this. So you're going to set up the gym environment, And here you can see we've imported the frozen lake gym environment, just set some of the seeds, and here's where you can you can enable those ice dynamics, but I do strongly recommend you set them to false and disable them just for this first lecture. You can have a look if you like, but the results won't make much sense. And then here we've just printed some of the initial environment states. So here you can see we've got frozen ground, which you can walk on, FFF, and then we've got some hot melted ice that if you fall in that you're gonna terminate, so that'll be game over. And you've got to get to this this ground state here where the frisbee is. So in here you can just see from the start state we should probably go right, then down, 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 and then right again. Alternatively, you could go down across this frozen ground, right a bit, then down again, and right. That would be two of the optimal solutions. So we're just running this next cell. We've got these actions, which are just integers, left, down, right, up, 0, 1, 2, 3. And then at any point we can go environment.reset resets the environment state, and then we can basically pass an action into the environment, and then it will tell us which state we've ended up. And in this case, we started off in this state here, and we said we want to take the action down, so we're going to end up in state 4. However, if you had these slippery on, you might end up in a different state. So you might end up sort of in the same state. You might end up in state 1. Even if you try to move downwards, there's some probability that you'll actually end up in this state by slipping on the ice and falling over. But we've disabled that, so there's this probability that we're going to end up in this state as our next state, and we're not terminated yet. We haven't found a frisbee yet. I've just made a helper function which helps us visualize what we're going to see later on. Okay, so you set up the environment now with some ice, and we're also going to just say that the policy that we want to evaluate now, because we're just doing planning, is going to be a random policy, and that's quite a nice one to start with. So we're just going to literally have our policy is going to be like the person is very, very, very drunk, and they're just going to always randomly go into one of the tiles. So it's just like wandering around completely drunkenly, randomly, with no planning, no good behavior, well experienced behavior developed yet. And we're going to just see how good that random policy is. So we can say there's a 1 in 4 chance of taking any of the actions. Okay, so in the collab code, if we just this is our policy. We've got the number of actions, and we're just going to divide ones by the number of actions. So in our case, our policy is just going to be a probability for every state of 0.25 of transitioning to left, down, up, or right accordingly. Okay, so this is the policy evaluation algorithm, and we're going to sort of run through this as we go through. But we start off by initializing our value function with zeros everywhere. So what we're going to do is we're going to iteratively apply the Bellman expectation equation, and you'll first notice that we're doing this for every state. So we're just going to go through every state here, and we're going to iteratively evaluate our policy, our random policy. Pi is this random policy, and we're going to do that by just iteratively applying this Bellman expectation equation. So you'll first of all see that the values are 0 pretty much everywhere apart from this one cell here where it's got a value of 0.25. So we're going to just see how that value in particular was calculated, and then we're going to look at some of the other values. So if we look at the Bellman expectation equation, if you remember it from the previous lectures, we evaluate the value for every state for this policy pi, for this random policy. And what it does is it goes through all of the actions. So we've got left, down, right, and up as our possible actions. And we look at the probability of taking an action conditional on being in some state for that policy. So we're just currently looking at this random policy, which means that this is always just going to be 0.25 because we're just randomly taking for any state we're in. We're just randomly 0.25% of the time going to go to one of those states. So there's a quarter probability of going left, down, up, or right. Then we times that by the action value function, q pi, under that policy. And we just get this definition from its definition, where we plug it in, we expand it out, which is here. And this tells us that it's the immediate reward plus the discounted value of transitioning into the next state by the environment transitional dynamics, which the MDP has. So let's just look at this 0.25 value here. So the immediate reward of being in this state is 0. There's no reward here. There's some reward over here, but there's nothing here. So it's 0 plus our discounting factor. We're just setting that to 1. Gamma is equal to 1. And then we're going to look at all of the next states that we could go to, we could transition to. And we're just using a deterministic policy for now. So this is just going to be 1, which means that once we've decided to take this action, we're always just going to take it. But actually, the MDP, the environment dynamics, can sometimes give you different probabilities in here. And this is where your ice slipping mechanics would come. In our case, it's just going to be 1 times the value of being in the next state. So there's no value being in this state. There's no value of being in this state. And if we go down, actually, the way the grid world is set up is that just throws you back to the current state. So if you go down, it just takes you back here. And there's no value being here. But if we were to take the action of going right, we would then get a value of 1. So because we've got a 0.25 probability under that policy of going right, that means that this whole thing just simplifies down to 0.25 times 1, which means our final value is 0.25. So the whole thing is computed by doing 0.25 times 0 plus 0.25 times 0 plus 0.25 times 0 plus 0.25 times 1, which gives us our final value. And then for all of the other states, there's no value from going in any of those positions. And this one here, you might think there's some value here, but this is a terminating state, so it's also got no value, because this is falling into the ice and falling into the water and terminating. So what we're going to do now is we're just going to iteratively apply that process to evaluate our policy. So this is just going to start flooding out numbers through this grid world, and we'll see it eventually does converge on the true value function. So that's iteration 1. Now we're going to do it again, move to iteration 2. We're just going to go through every state, and we're going to iteratively reapply this Bellman expectation equation. And again, it's easiest to just look at these starting states around here. But here we see, how do we get the value 0.06? And what we do is we see there's a 0.25 probability of going to any of its neighbor states. But this time, it can actually get that reward of 0.25 that we just previously calculated a quarter of the time. So we say that it's got a value of 0.25 for that policy, for this probability of going right. And then it's times the value of the next state in that case, which is 0.25. So the value of this is actually 0.25 times 0.25. So that's a quarter times a quarter, which is a 16th, which is 0.06. Is it 0.0625, I believe? You just can't see all the numbers here. It's a bit truncated. And then how is this value computed? Well, it's this time here. Again, there's a quarter probability. We can go left, up, right, or down. So we're going to compute it by doing, this is a bit of a long calculation, so bear with me. First of all, it's 0.025 times 0.0625 plus, so that's the probability of going left, plus 0.25 times, again, 0.0625 for going up. Now, if it goes down, it bounces back and gets the original reward of 0.25 again. So that's 0.25, so plus 0.25 times 0.25. And then if it goes right, it gets that juicy reward of 1 again, so plus 0.25 times 1. So if you put that all together, you get a value of 0.34375. There's quite a lot of calculation just to get this state here. So that's the second iteration. And basically you just keep iterating and it propagates out these values throughout the grid world. So I think that's enough examples for now. We just keep iterating through every state until nothing changes where it's reached convergence. Now, we don't really have time within a 50-minute lecture, but there's a very nice formal proof that if you do keep iterating, it actually does stabilize on the true value function for that policy. And if you're really interested, this is akin to the contraction mapping theorem, which is like if you start out with some initial estimate and if you just keep iterating, there's some inequality in there. So you're always going to improve by some very small bound. So because there's a unique solution, it is stable and it does converge. So this allows us just by iterating, by policy evaluation, we just keep iterating, we do actually get the true value function for that random policy. So now that we've got that true value function for that random policy, we probably want to know how to improve it. So this just shows like iterating 3 iterations, how it starts to propagate out, 4 iterations, it starts to propagate out. Then if you iterate it forever and ever and ever for this random policy, just look at these numbers amongst yourselves and think, just, is there some obvious way to do this? What would be a sensible thing to do? How would we actually improve this random policy given this value function for this policy? Go on, have a think. So how do we pick a better policy? For any given state, what we could do is we could just say our updated policy, our new policy, is just to choose the action which gives us the highest value. So we act greedily for each in a state. Which of these two numbers is larger? Is 0.016 larger or is 0.012 larger? Well, this is larger, so we would just always go down. That's our new policy. And here, which is larger, is it larger to go backwards or is it larger to go forwards? This value is larger than this value, so we could always just choose down again. And in this case, now it's going to say always go right. And in this case here, is this larger or is this larger? In which case it's here. Then this is larger here, so it's going to go this way. So we always just act greedily, we always just choose the maximum action. And as it turns out, in this very simple grid weld example, just that simple act of acting greedily does actually converge on the optimal policy. So you can see we start out with our random policy, we do our policy evaluation for that random policy an infinite number of times, and it converges on this stable solution, which is the true value function. Then we just act greedily, we choose the maximum action for each state, and we say that is our updated policy. And in this very, very simple case, that actually is the true optimal policy. Now, that's not always the case in cases where you have complex environment dynamics, like if you slip on the ice and fall over, or if you have much larger environments, you don't actually always just from a single improvement step get the optimal policy straight off that easily. But it does give you a way to always improve your policy. So you might now have some gut feeling of how we can build a control solution which actually helps us to find the best policy. And you'd be right if you were thinking we just put this in some outer loop where we evaluate the policies and then we act greedily, and then we reevaluate the policies and then we act greedily. That kind of approach forms the basis of modern reinforcement learning. So in this small grid weld, we did that just once. We started with that random policy and we iteratively applied the Bellman expectation equation to get the value function for it, b pi, and we just improved it once by acting greedily. Then we said that improving it once helped, but it didn't give us the optimal policy, this pi star. So now what we say is we could iterate that whole process. So we reevaluate the value function of the updated policy, then we improve the policy by acting greedily. And acting greedily just means we look ahead at the value function for each action and then you choose the best. And that really is the policy iteration algorithm. And it turns out, unlike in the previous case, that this actually does converge on the optimal policy, pi star, which is also the optimal value function, capital V star. And so now we know how to perfectly move on the ice. Now this actually converges on learning in a very elegant way to always perfectly navigate through the grid weld or through whatever environment. So the mountain hiker, this helps teach the optimal way to navigate the paths, to plan through the paths, to walk and to get to the summit without injury, with optimal efficiency and so on. And in general, we can say we now have our first solution to actually solve MDPs, our first solution method for MDPs. So a common question is, does it matter where you actually start? And well, with a bit of formula analysis, you can show that no matter where you start and what your policy is, you're always going to converge on the optimal policy. And this again relates to the uniqueness property of the optimal policy. Another common question is, does the improvement ever actually stop? Can you get stuck in some kind of local maximum? And as with the above, the formal answer is a bit beyond the scope of a 50-minute lecture, but it's covered in Sutton and Bartu if you're really interested. Conceptually, you can see that there's just two cases really, which are that either it's going to keep getting better and better and better, or it's going to stop. And if it stops, we want to know if it's achieved optimality. And if you write out the equality out, you'll see that stopping means that by definition you've ended up writing out the Bellman optimality equation, which means that if we've stopped, then you've actually reached optimality in the value space. So you have actually achieved the optimal policy. So just going to the Colab code, I'm now going to just show this policy evaluation process where we're just going to evaluate the random policy, and you can see it propagating these values through until it reaches a nice stable point where it converges. So it looks like it's starting to converge quite nicely now, so I'm just going to stop this. Actually, let's see if I can, how long did I say it should run for? Probably, yeah, it's just finished now. And now I've just got some code here which is just basically going to act greedily according to the action value function. So I'm just going to run these two functions, define them. This has really just got this max over the action values here, which I've just pulled out into a little separate function here. And then if you plot these, you'll see that in this very, very simple grid world case here, we do actually find the optimal policy very quickly. So this is just choosing the largest value, which is our optimal action, so the largest value from these states. And it converges quite nicely to the optimal policy. Now, if we have a much larger and more complex environment, so I'm going to move this onto an 8x8 grid world. Even so, I'm still not going to have environment dynamics just because I think the results are too unintuitive for most humans to comprehend. But here I'm just going to do this iterative process. So we're going to find our value function by just iteratively applying the Bellman expectation equations. Then we're going to just act greedily with that policy improvement function we wrote. And then we're going to just plot the policy here for this larger environment. You'll see now it hasn't actually learned the optimal policy just because we've just done that one step. Even though near the solution the results look quite good, as we move away from the solution you'll see some of these decisions are very stupid. So for example, this state here decides for whatever reason to move all the way up here, then all the way along here and all the way down here. It would be much more sensible to just go right and then take this much shorter path to reach the frisbee. So instead what we can do is we do policy iteration, which is where we're going to put that whole thing in an outer loop, and we're going to iteratively evaluate our policy. Then we're going to act greedily and improve our policy a little bit. Then we're going to iteratively reevaluate that new policy, that updated policy. Then we're going to act greedily with respect to it, and then iteratively reevaluate the slightly improved policy. And then we'll see this whole process actually does converge to the optimal policy, the optimal behavior. So let's just do this. This is our outer loop now. We've got this outer while loop, and we're just going to flip between evaluation and improvement. So now if we do this and we plot this, you'll see that we've now learnt what I believe is the optimal policy, and it looks very sensible to me quite quickly. So let's just look at some of these states. Again, now this is much more sensible. If it's here, it's going to quickly take this nice short path. If it's here, it's going to make a better decision to just go this way. And all of these, from whatever state it is, it looks like a very sensible direction to move along. So this is by this definition here. Before we were repeating for infinite times, weren't we? We were evaluating our policy until it converged, until it stops. And you may be asking yourself, do we really need to do so many iterative policy updates? Surely it's very slow to do that for convergence. Do we really need to do so many? And you'd be right if you did have that intuition or that gut feeling about this. And in fact, you can actually do just a very small number. Let's just say the number of updates we do is k. We could say k equals 3. So just do this amount of policy evaluation and then improve our policy. And in fact, you can just do like k equals 3 evaluation steps, then act greedily, and it will still converge to optimality, and it will give valid intermediate policies along the way. The exception is the case where k equals 1, so you just do one policy evaluation step and then one improvement step. And that's actually a special case which turns out to be equivalent to what's called value iteration, and it does actually converge on the optimal value function, but it doesn't have valid intermediate policies. So the takeaway from this is that there's this spectrum between how often you iterate the policies by the Bellman expectation equations before you act greedily. So, but they do all converge to the optimal value function from which you get the optimal policy. So this is value iteration in essence, and we'll see that it's very similar to policy iteration, but this time we're going to be mainly using the Bellman optimality equation. So we reapply the same process to policy iteration, but this time using this Bellman optimality equation here with this max in there. So looking at the algorithm, again, you'll see it's an iterative process. It's an iterative process, and it goes through every state in the environment. But now we compute the optimal value function for a state as the maximum action from the optimal action value function. So we sort of unroll that one step look ahead part, which gives us the optimal action value function, and then we just take the max over all of those action value pairs. And that's just, that whole process is repeated iteratively, and it kind of propagates its way backwards through the optimal value space. So this is like it's like the mountain hiker. It's like looking at where the summit is on the map and then slowly working their way back along the mountain trails and calculating the optimal shortest paths according to the terrain until they reach their current position. Or similarly, it's like if you got your frisbee on the frozen lake and then you can start at that frisbee location and you backtrack along the environment dynamics to work out the optimal way to avoid all of those melted puddles to reach your agent position. And each iteration is like going backwards a little bit more through the value space. So let's just have a look at some code to do that. So I've got here the value iteration algorithm, which optimizes the Bellman optimality equation. So if we just look through this code here, we still have this outer loop where we go through every state, but now we pull out the action value function. So we store our old value function and then we update it here. But the first thing we do is we find the Q values for all of the values for all of the states. So what does that mean? Well, if you remember, if we go back up to where we define that function, it takes as input the value function and the state where the current value function in the state, and then it just does this one step look ahead. So it basically expands out for all of the actions for that state. We look at all the ways we can go through the environment. So we look at what the reward is, just with that one step look ahead, and the probability of transitioning to the next state. So then we say what the Q value is for that action, which is equal to the probability of transitioning to that state according to the environment dynamics, so whether you slip on some ice or some other thing, times the immediate reward plus the discounted value of the next state. Okay, so that's just that definition from the equation substituted in. So it gives us the Q value for the action value for every action from that state. And then we just take the max overall of the Q values. And that's just a Bellman optimality equation. And then lastly, we have some convergence criteria here, just to say if the delta, if this change in action values is less than some small amount, then we know we've converged. So you may be asking yourself, like, this is a problem, right? Just iterating through every state in the environment. You can imagine like your Atari game where you've got many states. A lot of them you can't even observe just because there's thousands, millions, tens of millions, maybe even an infinite number of states in some cases. You can't possibly just go through all of those states like this. So yeah, there's a problem with dynamic programming. But in the next lecture, when we start looking at Monte Carlo methods, and then the subsequent lectures where we start looking at 2D methods, we have these new algorithms which don't need this loop here. Instead, what happens in these updated algorithms is they generally learn from episodes of experience. So they just start playing the game, and they start estimating the value of the state they're in, and then they start to learn to improve their policies just from episodes of experience. So that's what we'll be coming on to in the next lecture, where we start to really build full solutions to the reinforcement learning problem, not where we need these complete models of the environments, not where we need these transitional dynamics all provided for us. But let's just run this now. So this is the value iteration algorithm. We're just going to plot this, two variants of it, one where we can see like the actual values themselves. And yeah, again, you can see that was very fast, and the policy it's learned looks very sensible. It's just kind of backtracked its way through very efficiently. You've got all of these different choices for all of these states. This is just the same thing but without the values shown. But again, you can see these decisions here look quite sensible. This state here is kind of saying it can even go up or it can go down, and then follow this nice little short path to our goal. And this is just the equivalent expanded version here, which is more just the same as what's in the lecture slides. I've just taken that function and I've inlined it in the code so you can see it a little bit more clearly. But that's just our one-step look ahead where we compute the action value function. And yeah, it's the same thing. Okay. And there's kind of a few extensions to this. And first, I really highly recommend reading section 4.5 of the Sutton and Bartow book to really learn about asynchronous dynamic programming. It's really short and it only takes about 5 minutes. And also there's an interactive demo here by Andrzej Karpathy and Andrzej Karpathy, and he's really famous in the deep learning and reinforcement learning field, where he's in charge of Tesla's autopilot fleet. So in this demo, it gives you kind of a little bit more intuition behind like evaluating policies and doing these greedy updates. You can kind of click on these buttons here. You can see how it kind of iterates between, and you can see it kind of propagating through. You can actually click the cells and set the reward, so you can kind of explore and have a feel for that. You can also try doing things like evaluating your policy lots of times, and then you can just act greedily with respect to that, and then you can try evaluating this new improved policy and then acting greedily with respect to that, and just see how it converges. Or you can just toggle that immediate sort of step through each time, which is the value iteration algorithm, that k equals 1 case. So yeah, that kind of concludes this lecture. So in summary, dynamic programming solves the planning problem, but it doesn't solve the full reinforcement learning problem because we require direct access to the MDP. We need to know all of those transition dynamics that we can just get those probabilities for us. But in practice, we don't have access to all that data, so we need to sort of estimate and use approaches which can just sort of work in a way without requiring all of that complete knowledge. So yeah, dynamic programming requires a complete model of the environment, and policy evaluation solves the prediction problem, and then there's a spectrum between policy iteration and value iteration, and these solve the control problem, which allow us to find those optimal policies. There are some extensions like doing this asynchronously, which you can read about quickly here, and I do recommend you have a play with that demo. So yeah, that concludes this lecture. That's it. So hope you have a good week.